Today, we're going to talk about real-time mode from Databricks, which aims to take on Apache Flink for real-time streaming. With me today, I have Nav from Databricks' product team. Can you please give us an overview as to what real-time mode is?
Real-time mode is a new execution mode within the Spark structured streaming engine. Spark structured streaming has always been used for high throughput ETL analytical workloads. Real-time mode is a companion to what already exists. You can think of it as a new mode within the same engine that now lets you achieve ultra-low latency applications. So some of the best examples of this would be real-time fraud, instant personalization, or even curating real-time context for all of your AI agents. These are applications that require hundreds of milliseconds to even like double-digit millisecond latencies. And Spark real-time mode now makes that possible.
How does it compare to Flink?
At the outset, I'd like to say that Flink is a great engine. It has been the engine of choice for the past few years when it comes to real-time streaming application. With real-time mode, we're trying to address a very different customer need. The history behind this is that customers tell us that, hey, Spark is the preferred engine and the preferred platform for our analytical workloads. Our ML scientists use it for their experimentation, but it's only for these specific low latency sub-second use cases where we need to go and manage a separate engine called Flink. Now, there's a lot of complexity associated with it. Two engines typically means two different infra stacks to maintain, two billing systems, two different failure modes and observability metrics to kind of understand, and often two different engineering teams with very different expertise. That's a lot of complexity. So customers have told us, why do we need to kind of have these two engines? Can Spark solve this for us? And so real-time mode is basically a setting in Spark that makes it possible now for most real-time workloads to not need an engine like Flink. You can just use Spark for everything for these sort of workloads. So we've compared our real-time mode against Apache Flink. In our GA blog, as well as in a blog that we published last week, we shared some benchmarking of how real-time mode performs when it comes to latencies against Flink. And we found real-time mode is actually comparable on certain transformations to almost 100% better than Flink on some other transformations. So I would say from a performance standpoint, customers who use Flink can be able to replicate the same or even better performance on Spark real-time mode.
How does it compare on cost?
Low latency typically comes at the expense of cost. Latency and cost is always a trade-off, like with most things. But what we don't want to do is erode ROI for customers, because that's the core important thing. These are typically continuous pipelines that are always on, and you need them to be cost efficient. We have benchmarked Spark real-time mode against both Apache Flink as well as against the old Spark microbatch mode. And we have found we are extremely competitive on cost against Flink across the various transformations. So customers who are using Flink should not feel cost increasing if they use Spark real-time mode. And it's actually cheaper than microbatch mode when you try to achieve these sort of low latencies, which are sub-second. Typically, if you were to try to use the old microbatch mode and try to push latency to, let's call it single seconds or lower than that, you would have to oversubscribe the system and basically use a lot of compute. And real-time mode is a much efficient implementation of that. So our customers who ran microbatch mode and real-time mode in parallel found almost a 50% cost reduction compared to the old microbatch mode. And it is basically on par with Flink. So what you get with real-time mode is basically cost competitiveness, but much simpler APIs, much simpler implementation, and much lower operational costs.
Can you give us some examples of real customers that have already been using real-time mode?
So firstly, let me talk about what operational use cases are. Operational use cases are use cases where you have data, you need to make an immediate decision on the data and drive like a business decision or a business process. This is very different from analytical workloads where you're kind of storing historical data, running analysis, writing reports, maybe making some dashboard. These are actual live decisions that need to be made. So some of the top use cases that come to mind are real-time fraud detection. You can think of any financial service, any financial institution. There are payments that get processed. There are transactions that are made. You need to actually detect fraud for these sort of transactions in the order of milliseconds. Any later and you could basically go bankrupt. It's as simple as that. The other use cases are personalization. So e-commerce companies, travel companies, if you're going on their website, they want a highly personalized experience and they want it immediately personalized. For example, if you go onto a travel site and you have searched on that travel site previously, you would expect to be shown flights and hotels that you've kind of interacted with in those locations, not something that is completely drastically off or just like a vanilla plain context, right? And you want that fast. Like if you don't get that personalized experience in like a second or 2 seconds, you as a consumer would just like leave that site and go somewhere else. Agents, AI agents are truly changing the game. Like the new customer is an AI agent, and an AI agent requires extremely fresh context to be able to provide a grounded, well-reasoned answer. And preparing that context and having it available within milliseconds is critical for most customer bots that you kind of see on any application site. Now, in terms of real customers, we've shared a few examples in our GA blog that we published. I'm going to talk about them. So one of the big ones is Coinbase, obviously one of the biggest crypto exchanges in the world. For them, risk management and fraud detection is core to their business. Like if they fail to detect a fraudulent transaction, they could be out of like thousands to millions of dollars. And they need this to be done really quickly. So I'm talking sub 100 milliseconds in terms of detecting fraud. Now, how do they typically do this? They have an ML platform which computes what they call features. Features are essentially things that their ML models use to score risk and decide whether something is a fraudulent transaction or not. So the simplest example would be, from this user for the last minute or the last 5 minutes, what's the total transaction value that has happened? Okay, and you need that number. If it's above $1 million, you know there's some bot trying to attack your system, or it's something fraudulent. And so they need to maintain these sort of like rolling window aggregates with sub-second freshness. Now they have a unified ML platform where they're able to build all of these features on Spark and are able to achieve this in sub-second latencies. Another example in the same vein would be DraftKings, which is one of North America's biggest sports betting and gaming companies. And they basically need to detect fraud on bets that you place on games. And it's the same story over there. They are now able to build all of their features on Spark. Before this, they used to use Spark for offline features or batch features. So think of it as an ML scientist that is trying to do some experimentation on a model. They would use Spark to compute features and then train their models or test their models. But when you go to live inference, where you had to actually detect this in real time, they would need another specialized engine to kind of do this computation. Now they're able to use Spark for both the batch offline training part as well as the online inference part. And it has simplified their operational stack drastically. And the third example would be, there's this company called Make My Trip. For viewers in the US who might not be familiar with the name, this is one of Asia's biggest travel aggregators and travel sites. And they were one of the first customers to actually use real-time mode. They use it in two ways. So first, when you search on Make My Trip for a hotel or a flight, your experience is completely personalized. And that context to kind of personalize that experience is built using Spark real-time mode. And they also now are investing massively in AI agents to power their user experience on their applications. And all the context for that is also basically being powered using Spark real-time mode.
Now, before we jump into a demo, can you tell us a little bit more into the nitty-gritty technical details as to what it is doing under the hood?
Yeah, absolutely. I'd love to do that. So some context before we talk about the actual architectural innovations that are powering real-time mode. So The original architecture of Spark structured streaming, it's called the micro batch mode architecture. We've written about it a lot. There are a bunch of blogs published about it. But at a high level, what it does is it takes an input stream, it chunks it into discretized chunks called micro batches, small micro batches, and then it processes these micro batches. This architecture is actually what makes it possible to do really high throughput ETL, because you're kind of batching and you're kind of getting the efficiencies of batching. But this architecture also makes it difficult to get true sub-second, millisecond level latencies, because you are at the end of the day batching and processing it. So there are three things that we did in this new execution mode called real-time mode. It's an architectural evolution rather than like a new architecture, but there are three things that we did. The first thing is we actually process events as they come in. So unlike micro batch mode where we are dealing with these discretized batches, you are now having a continuous data flow. So as an event comes in, the event gets processed immediately by Spark. So that automatically helps reduce some of your latencies. The second thing we do is what we call concurrent scheduling. So what this means is that if you take a query typically has multiple stages. You can think of it as like there could be a single stage query, like a stateless query, or multiple stages if you're kind of doing some sort of a filtering followed by an aggregation. And these stages in the old architecture used to basically get processed sequentially. Now all these stages are always on and concurrently on. The right analogy for this would be if you go to a car wash, right? Let's say your car goes in, first it gets rinsed, then it gets soaped, then it gets rinsed again, and then it gets dried, and then it gets out of the car wash. It's only once your car gets out of the car wash that the second car come in and start the process. This is kind of how micro batch mode used to operate. With real-time mode, we made this into a conveyor line, a true assembly conveyor line. So once your car goes through the first station, the first station is available for the second car to go. So you're kind of optimizing that scheduling of the stages and really running everything concurrently. And the third thing we did was actually more of a hardware level innovation, which is around shuffles. So shuffles are the most costly part of any streaming query plan. A shuffle is when, let's say, you need to kind of redistribute data across the network because let's say you're doing an aggregate by user ID, you want all of the orders for a specific user to be processed by one worker, right? So you want to kind of distribute all the orders that you have seen for that user and send that to one machine. That shuffle is costly and that takes a lot of latency. But one of the most critical parts of that shuffle latency is actually the way the shuffle mechanism works. Previously, once a worker was done processing and had the output ready, it would write to the disk in your machine, and then the output would get picked out of that disk and sent to the reducer machine. So there's a mapper and a reducer. Mapper gets done, it writes to the disk. Now the reducer picks from the disk and then starts processing. These disk-based writes are naturally the slowest part of how your computer works. We have like completely eliminated this disk-based shuffle mechanism. Now there's like a continuous connection. There's an in-memory continuous shuffle that happens. So the mapper basically sends data continuously as it's done to the reducer in memory. So you're completely eliminating the need to write and read and write from disk, which helps save a bunch of your latency. We call this the new streaming shuffle. And these three things together are basically what is powering the sub-second latencies that you're kind of seeing in real-time mode.
Jump into the demo.
So I'm going to show you a demo that is for an e-commerce orders or e-commerce events pipeline. Think of an e-commerce company that is basically recording each of its orders across the world. These are events that basically flood through some sort of an event processing message bus. In this case, I've modeled it in terms of a Kafka topic that is receiving all of the e-commerce events. The Kafka topic is basically being read by Spark, and we're going to process each and every e-commerce event, and we're going to flag high-value events. We're going to detect high-value events in sub-second latencies and even lower, as you will see. And we're going to write it back to another Kafka topic, which will basically now contain all the flagged events, which can basically be sent to a separate processing system or for human review or things like that. But you're basically able to detect this in, let's call it subsecond or hundreds of milliseconds. So let's first start by just looking at the data, the schema of the data and what we're dealing with. So like I said, this data is basically getting pushed to a Kafka topic. What I've done on this screen is done a batch read of the Kafka topic and looked at the top 20 events. So you can just see the latest 20 events in the Kafka topic. And let's look at a single row here. So this tells you what each row or each transaction is. So it's an e-commerce order. There's an order ID. There's what the product was, in this case, a laptop, the category associated with it. In this case, it's an accessory of the laptop. The region from which this e-commerce event originated, in this case, is US East. What's the value associated with the transaction, and the timestamp at which this was generated. And each of these rows are individual orders with these set of details. Now, let's now move to the actual Spark streaming and real-time mode part of this demo. So the first thing we do is kind of read this data from the Kafka topic. So I've set up this code. This basically, it reads from the Kafka topic. So there's a spark.read stream format Kafka, and I'm reading from that specific input topic. And like I said, my goal is to filter the data and identify high value events. So I have a filter condition, which is basically, I'm filtering for the amount. I'm saying, hey, things with a value of $500 and above are high value. And I'm also interested, let's say, in electronics. I'm only interested in category of electronics because those are the ones that I want to focus on. And so all this does is it reads from Kafka and it applies this filter. At this point, I just want to say there's nothing different that I've done which is specifically related to real-time mode. This is exactly how you would write a Spark structured streaming query traditionally. I have not done anything different. And right now, this condition is a simple filter, but you can model it to be anything you want. It could be a complex windowed aggregation that you want to do, or if you have some custom transformation logic in a UDF, you can plug that in just as you would have done in any Spark structured streaming query before. Now, after we define this filter, we move to the right side, which is basically we're writing to the Kafka output topic. And this is where the RTM bit of it actually starts playing in. So this is my RTM query where I am basically doing a write stream, same format Kafka, because I'm writing to our output topic in Kafka. And I have added one nuance to this, which is this new condition called the trigger being real time. And this is literally the only change I would make compared to writing a standard structured streaming query in microbatch mode. And what this tells Spark structured streaming is basically to run this query, which is the same query, written the same code with the same APIs, but in real-time mode, and use this new optimized execution engine. And Spark automatically recognizes that, hey, you want to optimize for latency and you want to run this query, and it basically runs. As a user, you don't, if you've ever used Spark, this is the easiest thing in the world, because all you have to do, you've not changed the way you've coded your business logic, you've not changed the way you've kind of expressed your transformations. All you've done is change one flag or one configuration, which is your trigger type, to real-time mode. And you will now be able to get basically sub-second latencies associated with it. Now, what I've done is I've already written the metrics associated with this query to a Delta table and kind of populated it. And I'm just going to pan to that dashboard where I basically show this. And so this is a job that I basically ran for an hour, okay, before this meeting. And I wanted to show that, hey, not only do you get it immediately in terms of like latencies, but it's actually consistent across time. And you can see that this is basically the end-to-end latencies that you're calculating from the time the event hit Kafka input topic to the time that Spark basically finished processing and started writing to your output topic. And there are two bars over here. I like to focus on both of these. The yellow bar is basically the average latency. So we call it the P50 latency. As you can see, this is incredibly consistent. It's like 4 milliseconds to do this. Essentially, you're basically, from the time the event landed in your Kafka input topic, Spark processed it, identified it, and started writing. It's just taken 4 seconds to do this. And the blue bar over here is the P99 latency. So this is like the 99th percentile of events that you're kind of seeing. And even this, you're like, it never crosses more than 100 milliseconds. So you're like well within sub-second latencies, which typically what companies target. You are basically now at sub 100 millisecond, but like most of the time you're like sub 50 millisecond on these P99 latencies, which is just incredible. Like if you had ever written this query or this implementation without real-time mode, it would typically take you multiple seconds to get there, and you would have to go and like learn Flink, hire a new team, figure out their billing system, their infra stack, just to get this sort of sub millisecond latencies. We have simplified the entire process. We're saying you don't need to do any of that. All you need to do is change one flag on your existing query and you're able to get to this latencies.
What now? I guess it's GA as of today?
Yep, it is GA. It is available now for every customer. We have spent, so this feature was in public preview in August 2025. We've spent the last 6 months really battle testing it, hardening it, making it available across different clouds, across different access modes when it comes to compute. Now it's available for everyone to use. I would say we're continuing to improve the feature. So we're continuing to, our focus is there's a regular goal to kind of bring these latencies down, continue to optimize on costs. Our goal is to actually beat any other engine out there on both latency and cost. So there are going to be continuous investments in that. There are certain edge cases that we don't support in the spirit of being completely honest. Like there are certain operators, like the biggest one being stream join. Like RTM does not support that yet. We are working on that actively. It's in development. You will see those coming out pretty soon in the next few months or so. And yeah, that's the plan. We're hoping that customers are able to test this out, use it, and give us more feedback. And it's going to be a super important part of Spark structured streaming going forward.
Thank you so very much for your time, Nav. Truly appreciate it.
Yeah, you're welcome. Thank you for the opportunity to talk to you guys about real-time mode.